everyone, it's Erin from the Robot Missions Lab. Today we have an experiment about the timing accuracy of a microcontroller. There's going to be two signals being driven 180 degrees out of phase with each other, and we'll be controlling these using 4 different methods that we're going to be comparing. And in order to investigate the timing, we'll observe the period duration of these signals and analyze the differences for each of the different methods. So why exactly is this useful to know? So some output devices depend on these waveforms occurring at a specific time. For example, with one pulse happening at an exact time from the previous pulse. An example is with stepper motors. The pulses have to be sent in a sequence, and by adjusting the timing, it enables microsteps, which gives you more precise movement at the output. So here's the setup of the experiment. Observe this bundle of orange wires behind me. It uses a STM32 L4 discovery board, and there are 4 LEDs connected to the corresponding output signals, because it was designed in mind with a stepper motor. Now, in order to observe these signals, we'll be using the Moku lab, but there's only 2 channels available, so we'll be looking at the signals for the first and the last LED. The 4 methods that are being used are a cascade of timers using the internal triggering system, as well a single timer, some blocking delays in the while loop, and then checking tick in while. The hardware clock rate is first set to 16 MHz, where the prescaler is then decreased. In later tests, the clock rate is also increased to the maximum. Before diving into the details, here's a summary of the results. What was being measured was the duration of the period of the combined waveform, meaning for both LEDs. The standard deviation was used to compare each of the methods from approximately 100 counts. Method 1, the internal trigger timers, was the winner for the majority of tests, even as it got progressively faster at 16 MHz. Except for 2 cases where method 2, the single timer, actually beat it. This happened where the clock was 16 MHz and 48 MHz, with the prescaler being 1. Method 1 then narrowly beat method 2 at 80 MHz, which was the maximum clock rate for this chip, with 7 nanoseconds difference on the standard deviation. Wow, the excitement is just like a sporting game. Now let's hear about each of the 4 methods. There is a small correction to make, which is in the introduction I said that the signals are out of phase by 180 degrees. However, that's not the case. They're out of phase by 90 degrees. In fact, here's a little illustration of what will be seen and how it's set up. So this is showing the waveforms of the LED pulses and the combined waveform. So here is what the combined waveform represents when the first LED is on, then the second, then the first one is off, then the second one is off. And you can see that with this overlapping photo or drawing right here. Here's why combining 4 of the waveforms would not work for this analysis. So imagine those 4 waveforms are the signals for those LEDs, and then we can have them sort of stacked on top of each other like that. Then when we combine all of those or add them together, we wouldn't be able to tell when the signal that is colored green and the signal that is colored blue are changing, and then the same for purple and orange. So due to this overlap with the rising and the falling, it wouldn't give us the details that we would need to see all four of those LEDs. There will be a further discussion about this and the tools for analysis later on in the video in the discussion section. But this is also why for 2 channels we're just monitoring the first and the last LED in the sequence. So this first method uses timer interconnect triggers. This means that there is one timer that then starts a cascade of timers following it, and it does so using these internal trigger connections. Inside of the reference manual for the chip that you're using, there is a table in here that shows all of these internal trigger connections. So for example, if we are to select timer 3, then like say right here, then we know that on the internal trigger connection number 2, it's then attached to timer 2. So with all of these internal trigger connections, then you can set the next timer to listen for that internal trigger connection, and then once it receives that, then it starts that timer. And in doing so, you can then make a series of timers that then start once the one previous to it has activated that internal trigger connection. So that activation is usually done with something called an output compare register. Now the LEDs that you see blinking behind me, they are actually being activated also by this output control register. There's 2 kinds of output control registers that you can have. One where it activates the output on that given channel for that given pin of that timer, and then another one where it specifies no output, so output compare no output. And likely for the majority of cases you probably wouldn't need the output, so you would likely select the no output for that. Before we get too ahead of ourselves, we still have to discuss how the cascade of timers was chosen and sort of figured out. So the method of doing so here was to start by making a diagram for which timers feed the dependent timer, and then mark the ITR, that is the connection that they use above that. So there, to start before that, step number 0, not 1, is to actually determine the timers that are available. So this was done by looking at the user manual of the board, and this board has an Arduino style header pinout on it. And so with this, I was able to see which timers were available on these pins that can be easily accessed. So here we could see there's a timer 3, 2, 8, and 4, and another few of 8 that have different channels available. So the goal here was to choose the ones that are the channels without the N, so it's just the regular timer channel, and then that resulted in these sort of graphs here where it maps out the timers and the dependent ones that are available with the given ITR. So that was basically mapping out this table to figure out that. Then it was mapping out the path for each master option. So the timer, that would be the starting one, just like mapping out the path. So for example, with 8, if we start with 8, then where could it go? It can go to either 4 or 2, okay? And then based off of 4, then where could it go? Well, we can see up here we have 2 options. We can't go back to 8, so we can go to 2 or 3. And then if we go to 2 or 3, then what could we do? Well, if we go to 3, where we actually don't have any options left because it's either 2 or 4, and oops, sorry, I misspoke there. We could go back to 2. Why didn't I think of that earlier? Anyway. That's kind of funny. Oh wait, sorry. Scratch that. Okay. So the reason why this one would not work is because it uses the same ITR. So if we wanted to call all both of these timers at the same time, 4 and 3, then sure, could go for that since it uses the same ITR. But that's not what we want. We want separate ITRs and separate timers. Okay, so then let's see. We can start with 8, go to 2, and we run into the same thing where it's the same ITR. Okay, so now let's see. What about 4? Yeah, we could do 4. Well, what about 2? This is the result of 2, and then we noted that once we get to this path, well, for 8, we already know that that won't work. And that's sort of a similar situation for what 4 was as well. Now we'll skip ahead a lot and we'll just say, what about 3? Okay, here is 3. So 3 can then activate timer 2 via ITR 2. 2 can activate timer 8 via ITR 1, and then timer 8 can activate timer 4 via ITR 3. As a bit of a side note, what was interesting while developing this and figuring it out, that sequence of numbers, like for example 3, 2, 8, 4, by looking at it enough times, sort of memorized it. So it's funny how it's also a 4-digit number, but anyway, there could be creative uses for that. Okay, back on track. So now we have this sequence of timers that we can use for the timer connects. This is showing the setup of the pins. So based off of the timers that are used, this is just all about okay. Here is the setup of the pins that are used for the LEDs based off of the timers that are used. This was about searching through the user manual and likely the reference manual as well, just to determine the pin numbers and what they correspond to on the Arduino headers. A little bit of behind the scenes here. This was some notes from analysis and debugging to make sure that the timing was correct. Lots of timer markers on the oscilloscope and annotating it as well. The reason for those voltage drops was because in the early version of the setup I skipped using the resistors. I was sort of in a rush, so that's why there was that voltage drop. One more thing to note when you're looking at the reference manual for these timer interconnect triggers, the tables are different depending on what type of timer it is. So for example, timer 8 is an advanced timer and the table below it are regular timers. This will come up later when discussing about the setup of the timers. Okay, now let's talk about the setup of the timers. I'm going to show this display of screenshots here first, and then we'll dive into STM32 IDE. Alright, so here you can see the sequence of timers. It goes from 3, 2, 8, and 4. So 3 is the one that's starting the next one. It's the main one, sort of in charge there. So let's see. Here are some interesting things about how this is set up. So you can see here that on channel 2, right here, this is the one that's set up as the output compare. So when we want to activate that ITR, that's talking about this, the trigger output. And then in that you have this parameter called trigger event selection, and you can choose output compare, and then we're using output compare 2. So we use OC2 ref for this. Here are the settings of that output compare. So there are different types of modes. This is set up as just toggle on match. And then we have the pulse, and this is just used for the timing of when that output compare is triggered. So that sort of offset for when it's trying to count up to that ARR auto reload register counts up to there, and when it reaches this number, then that's when it triggers the next timer to go. So when we're talking about the next timer, then how does it know when to start? Well, it has right here the mode, so it is in this mode of the cascade, and then the trigger source right here is ITR2. So we know it is called ITR2 because we looked up in the table from earlier that 3 can go to timer 2 from the ITR2, and we'll just look up at that table again. Here we go. So timer 2 is looking for timer 3 on ITR2. And there we have it, right? So this is how that timer is listening to the other timer. yeah, it can get a little bit confusing sometimes. But if you take it just step by step, you can make it work. Alright. So then, a similar setup to the previous timer, we want to have an output compare on one of the channels to trigger the next timer. And here we see that same thing again. The trigger event selection will be the output compare on channel 1. And then here are the settings for that, which is the same as before because we're having them all be the same. But this shows that you could make it different if you wanted. If you wanted one timer to be offset by a certain period of time compared to the other one, then yeah, you could definitely make that. Now here comes the tricky part, because timer 8 is that advanced timer that I pointed out earlier. So here we have the trigger sources ITR1, which we could find in that table that I just showed. And what makes timer 8 a little bit different than the previous ones is that, well, for some reason there are 2 trigger event selections, and the way that I was able to get it to have the correct polarity was to have it be the opposite. So the ones previous to it, the polarity is high, and this one is low, but in reality the LED lights up and you get that sequence of light as expected. This is something that could have further investigation as to the reasons behind why it does this. However, I was mainly focused on making this work, so I didn't do too much investigation into that. I just figured this would change it, and it did. And interestingly enough, the timer that 8 connects to is timer 4. It's back to being a general timer, and setup is similar to the previous ones. However, this one, its polarity also had to be low. So there are different reasons why this could be. For example, with 8 we had the 2 triggers, and also the mode is toggle, so perhaps that has something to do with it. Anyway, this could require further investigation if needed, but it was able to be working by just changing that polarity. Okay, so that's what it looks like from all of those screenshots together, but now we can actually look at the IDE and see it in here. So just to show a little bit of what it looks like. Alright, so here we are in the device configuration tool aspect of the IDE things. So here, for example, we could search for TIM3, let's see, channel 2. And here we will see that this one is the one that we use as the output compare register, and also the output for the LEDs, and it's on PV5, and yeah, it's configured as that TIM3 channel 2. Okay, now let's look at the timers. So this is just what it looks like in the IDE. The numbers changed a little bit from the screenshots that were shown. 3, 2, and then 8, and then 4. And then if we are to look at the code, what you'll see is actually kind of the absence of some code. So for example, this is the main portion, so the callbacks are empty, and all that we do is we start the timer, we enable interrupt on the trigger in case we needed it, and then we start the output compare, and here we go. While is empty because the timers are doing everything on their own. And this is all just the initialization. Okay, that wraps up method number 1. Now let's discuss method number 2. Method number 2 uses a single timer to count up to a certain amount of time. Then it calls an interrupt. Inside of that interrupt, it checks how many times it has been called, basically creating a counter, and based off of that counter, it determines if LED 1 should be on or off, or if the fourth LED or the last LED should be on or off as well. Then in the main while loop is when those flags are checked and the HAL is called to set those LEDs on or off based off of that. So let's see what it looks like in the IDE. So here we have TIM2 was used because TIM3 and TIM4 are the pins for the first and last LED, and TIM8 is an advanced timer, so just going with TIM2 for this. The source is the internal clock, which is 16 megahertz, and here you can see the prescaler and then the counter. So for example, the counter is 2000, and that is the same amount as the output compare from method 1, sort of that offset. So we're still using the same timings, if you will. Then we can see in here that the interrupt is selected. Okay, so here we go. Inside of this interrupt, here's what I was trying to explain with that counter. So it counts up to 4 and then it resets. And based off of that count, it's either setting the LED on or off for each of those two. Those are flags, and those flags are then used in the while loop to set the LEDs on or off. That's it for method 2. It's a bit simpler than the previous method. Method number 3 controls the outputs directly from the main while loop. So these are set as outputs, and then in the while loop we're turning them on or off based off of either a delay or waiting for a certain tick from the system timer to pass. So here you can see in the pin setup there is the first LED and then the last LED with a sort of name to make it a little bit easier. This is the same setup for method number 3 and 4, but we'll go into each of them in the code. Okay, so here you can see demo equals 1 or demo equals 2. So 1 is method number 3 and 2 is method number 4. We'll start with number 3. So method number 3 is simply turning on and off the LEDs and then waiting that delay time. And the delay time is just given up here to make it simpler to read, so it's all in one spot. Don't worry. No, it should be lesser. Anyway, here it is. So it's just turning on and off the LEDs and waiting. So what's particularly bad about method number 3 is that it is blocking. So if there was to be any other code in this program, it would have to wait until all of this is done before it started. Okay, now to describe method number 4. So method number 4 is similar to the above. However, what we're doing is we are incrementing the count, that sort of like how we saw from method number 2, based off of whenever the tick time from the last tick time exceeds that delay period, which is 125 for this example. 125 milliseconds. So yeah, here you can see it increments that counter, and then based off of the counter, the flags are set for turning on or off the two LEDs, and then the LEDs are set accordingly. Okay, this completes the section about the method and describing all 4 methods. And now, here are the results. First, we'll look at this table and see the data that was collected for each of the tests. So here you can see that there were 6 tests in total, and the 4 methods were used for the first 3 tests, and then from tests 4 through 6 it was the second method, or the 2 methods. Now, since the count for counting the number for the standard deviation wasn't able to be controlled, it is noted over here, and for the purposes of the results, we are approximating this to 100 and just calculating based off of that number. Now I'll show you behind the scenes of gathering these results and the data. Alright, so here we have what it looks like in the oscilloscope view on the Moku lab. So this is what was occurring for each of the different methods. So maybe to first give a little bit of an overview here, like what is actually being measured. So it's from the start of this combined waveform where LED 1 is on and then LED 2 is off. And so it's from that starting point when it hits that rising edge to the very end. So essentially we are measuring the period duration. Now the Moku lab oscilloscope does have numerous types of measurements that can be used, and you can see those here. The reason for going with the period duration instead of, say, the duty cycle or the pulse width or negative width was in order to be able to capture what would happen if, say, one of the pulses started a little bit later and then it affects the entire waveform. Now, in terms of what was used in order to compare the different methods, that was the standard deviation. And as a little bit of a review, rather, The wider the spread is from the mean, then the larger the standard deviation. And this is measured in the same unit that was measured for everything else. In this case, it is time. So here you can see the standard deviation appears in this analysis table that can be used for these different modes of measurement. So the capture was taken approximately when the count was 100. The yellow waveform represents the combined of the two channels. So this was done for each of the methods. The difference between the first 4 tests was scaling down the prescaler by 10 each time. And that was also reflected in the delay and the tick check in the while loop methods of C and D. Then in test 4, it's now just method A and method B that are being compared. And you can see here the timing is getting a bit smaller. And in test 6 is where we hit the nanosecond mark even. Okay. So let's actually take a look at the tests in this table. So for test number 1, this was just the basic starting point of the test. So starting at 16 megahertz with the prescaler being 1000. And what we saw was that the method number 4 was actually the closest to method number 1 in terms of the delta of the standard deviation. And this is measured in microseconds. Then for test number 2, it was pretty close all across the board. The closest one was the checking the systtic method in the while loop. Test number 3, again, it's pretty close all across the board, and this is even in nanoseconds. Method 4 was very close to method 1, and method 2 is pretty close as well. Now, starting with test number 4 is where we start to see interesting change. So here we see that method number 2 actually beat method number 1 by about almost 70 nanoseconds. Test number 5 was extremely close, where the difference was only 1.6 nanoseconds. And then finally with test number 6 is where there was a larger difference. And luckily with test number 6, it is confirmed that the count was exactly the same. So this was one of the better ones because it is exactly the same count. So it is with a bit more confidence compared to, say, 102 versus 104. But here we see method 1 was the one that won, and it did so by a mere 7 nanoseconds. All of this data was just typed in essentially from those screenshot captures of the oscilloscope. In the discussion section, there's going to be a portion about different methods of obtaining this data that might be better. So let's sort of put this into perspective here. So looked up the timing of WS2812, also known as a neopixel, and for its pulses, it requires the microseconds mark, ranging from the smallest of 0.35 to the largest being 0.9 microseconds. And this timing can be plus or minus 150 nanoseconds. So if we look here, what is the time scale exactly? So microseconds are larger than nanoseconds, meaning that nanoseconds are smaller. So if we go back here to the results, nanoseconds being the smallest, this is quite a small difference in the grand scheme of things, especially here where it's only 1.67 nanoseconds of difference. This has to be considered when judging these results. Test number 2 is when it was still in microseconds, so that does give, I guess, a bit of a better look at it for sort of, I guess, a little bit slower. Anyway, let's hop back to over here. So something else to give this a little bit of perspective is HDMI. So HDMI requires 250 megahertz timing, and that would equate to 1,000 nanoseconds for the period, or 1 microsecond for the period. So if we go back here, HDMI is 1 microsecond for its period, so that also gives some perspective to this and the likelihood reality of it in this type of a project. What about the oscilloscope? The oscilloscope measures at 200 megahertz, which is 5 nanoseconds. And if Nyquist applies here, that would mean 10 nanoseconds for the period. So this also has to be taken into account when looking at these results as well. However, they are below 10 nanoseconds. They are greater than 10 nanoseconds, except for that last one and this one. So except for the final two tests, test number 5 and 6. And yeah, so this is just to give some perspective to these results, and if they can be deemed to be of sound finding or not. With that being said, let's discuss some of these pertinent points. In this experiment setup, the only thing that the microcontroller is doing is blinking the LEDs. This is a large caveat. In the real world, it would be unlikely that all the embedded system is doing is blinking 4 LEDs. The system would likely also be sampling sensor inputs, processing that data, and perhaps some communication as well. With all those other tasks, it would likely impact the timing of those 4 methods we just discussed. Also, there's always different ways of going about solving a problem. For example, an external clock, such as an RTC or an oscillator, could be used for more precise and accurate timing. Or the GPS module could also return the time from satellites in space, which would eliminate the risk of temperature variations affecting the clock on your system. There's also different ways of analyzing the results. For example, using the data from the oscilloscope mode on the Moku lab was useful to get the relevant information quickly, such as the standard deviation, the minimum and maximum. Yet there could be discrepancies based off of the number of samples to get those pieces of data, as that wasn't able to be controlled. To dive into the data more closely, the data logging instrument could have been used with further analysis in Excel or R or similar. Also, a totally different piece of test equipment could have been used altogether, and that would be a logic analyzer. It would also be able to monitor more than 2 channels, so it would allow for a more extensive test with all 4 signals for all 4 LEDs. In conclusion, this experiment applied concepts from embedded systems programming to analyze the timing of 4 different methods for controlling output signals. Based on the results, further testing could be done to see the performance in more complex systems. Thanks for tuning in to my Robot Missions Lab. Until next time, safe journeys for wild robot adventures.